Hello guys, in this video I'll be talking about retrosynthesis of complex molecules. And previously I made bunch of videos, more than 10 or 12 videos about retrosynthesis, and I have followed the Clayton book for retrosynthesis, as well as I'm following the Stuart Warren book. So whatever the examples today I'm going to describe in this video, they are all taken from the Stuart Warren book. And previously, if you are a beginner about retrosynthesis and you don't know what is retrosynthesis and what does it mean, then please go and watch my previous videos about retrosynthesis, where I have described the basic definitions, basic techniques, basic tricks for the retrosynthesis. But there's a one standout principle that stands alone in the retrosynthesis is whenever you are given any molecule, try to first recognize the functional groups and then try to count the relationship between the two functional groups. Either it is 1-1 functionalized compounds, or it is 1-2 functionalized compounds, or it is 1-3 difunctionalized, or it's 1-4 relationship, or it's 1-5 or 1-6, even 1-7. So that is the first and most important principle in retrosynthesis. So previously I made many videos about retrosynthesis, and where I have described a bunch of examples, heaps of examples about retrosynthesis. So today we will continue to do that, and that will be from the Stuart Warren book. And this is our target molecule 169. Okay, so first you look at the molecule. Okay, let me pick my pen. Maybe a pen. So first you look at the molecule is step 1. Then after that you recognize that functional group that are present in this compound is cyclic ether, that is containing 2 oxygens, that is cyclic ether, and that is also called acetal cyclic ether or cyclic ether. Okay, or it's also called acetal, and moreover this is used as a protecting group for the carbonyl compounds, particularly aldehyde and ketones. So the functionality present in this molecule is cyclic ether. That is the step 1 that we must start from. When we do beginning of the retrosynthesis, we first recognized what kind of functional group is present. Now, as you have already recognized that it contains cyclic ether as a functional group, the second thing that should come into your mind is that how we disconnect cyclic ethers. So the disconnection of cyclic ethers is basically the bond breakage from bond broken from carbon to oxygen and from carbon to oxygen. So the 2 oxygens, this one and this one, they are connected with the same carbon. Alright, that is the carbon which joins 2 oxygens. So this carbon is connected with this oxygen and this carbon is connected with this oxygen. So we cut these 2 lines. Now the right hand side gets the this oxygen gets the hydrogen and becomes alcohol, and this oxygen also gets the hydrogen and becomes alcohol. Now if you count the relationship between these 2 functional groups, it's 1-2 difunctionalized alcohols. And if you look at this compound, this functionality, this is acetone. So as I mentioned in my starting, that acetals are used as the protecting groups for the ketones as well as aldehydes. So in order to protect acetaldehydes or ketones, one must react acetone, aldehyde or ketone with diols. So these are the 1-2 diols. They react with ketone to give you this compound. So in forward direction, they react together and will give you this compound. So this is a retrosynthetic arrow, and this is FGI, means functional group interconversion. So which functional group is converted? So this was cyclic ether. Now there is a conversion of this functional group into ketone and alcohols. Next step is another FGI. Now think about how we can prepare diols. Diols can be synthesized from alkenes. So we disconnect the bond between carbon and oxygen again. This is the disconnection. Our FGI, we convert this OH group, two OH groups into double bond, that is the double bond. So when you do hydroxylation with osmium tetroxide or KMnO4, you will get this product. Next is Wittig reaction, Wittig cut, or Wittig disconnection. Why? Because as we know that Wittig reaction is used to prepare alkenes starting from aldehyde or ketones. By the way, if you are not familiar with the Wittig reaction, then I would recommend you guys to go into my playlist, which is name reactions, and if you go into that playlist, you will find number of name reactions in that playlist, and you can find the Wittig reaction as well. And I have made 5 or 6 videos about Wittig reaction where I discussed almost all the aspects of Wittig reaction, including the stereochemistry of Wittig reaction. And then you can learn about Wittig reaction and then come back to this video if you want. But if you already know Wittig reaction, then let's go to do more retrosynthesis. So the Wittig reaction is used to prepare alkene. So we disconnect the double bond between carbon and carbon. As you know, this is the carbon, this one, and also this is the carbon. Okay, so there's a double bond between these two carbons, that is alkene. Now we disconnect this double bond, and the one side becomes aldehyde and the other side becomes the alkyl halide. These are the starting material. Now if you look at this compound and count the relationship between these functional groups, so aldehyde carbon is 1, 2, this is CH2 3, and this is 4, and this ketone is 5. So the relationship between two carbonyl groups is 1,5. The 1,5 dicarbonyl compounds, one is aldehyde and another is ketone, but the distance between two functional groups is 1,5. Now what we can do is we can disconnect the carbon-carbon bond between carbon 3 and 4, and one side becomes acetone and the other side will become the Michael acceptor. So this is the electrophilic part and this will act as a nucleophilic part. So what we do, control needed, because we want to generate an enolate negative charge on this carbon. So in order to stabilize this negative charge, we put extra ester. That's the extra ester that we are putting for the stabilization of this negative charge. So this was the retrosynthesis up until here. Now let's move on to the synthesis of this, starting from these two starting materials. So you can see the beauty of retrosynthesis is that we can prepare such big and complex molecules from starting materials like these, acetone. Okay, so we have added extra ester, and then at the end of the synthesis we can remove this extra ester. The purpose of adding this ester functionality in the acetone is to provide a stability to the negative charge. So this is a ethoxide. This will act as a base. As you know now, this CH2 is called active methylene because it contains two labile hydrogens or two acidic hydrogens. Now what happens, this base goes on and picks this proton and generates a negative charge here, and then this negative charge goes on to attack this carbon, and then this double bond is shifted towards this carbon, and the oxygen of this carbonyl group, ester, goes in this way and then reverts back this one to give you this product. Now as you know that we have couple of ester functionalities now left, we need to first protect this ketone with acetal, that is this one acetal. We react it with glycol 1,2-diol, and then we remove this extra ester by decarboxylation reaction. So decarboxylation is reacting in the presence of a base and a high heat. First ester will be converted into carboxylic acid, and then that carboxylic acid will be decarboxylated with the heat. And in the next step, you reduce this ester with lithium aluminum hydride. So here lithium aluminum hydride acts as a reducing agent, and then after the reduction of ester, you will get the alcohol as a product, and then you will oxidize that alcohol into aldehyde using CrO3, that is put chromium oxide. So this is your oxidizing agent CrO3 that converts alcohols into OA. We call it oxidizing agent, and this is Ra, this is called reducing agent. So the purpose of this oxidizing agent is to convert alcohol into aldehyde. So initially what happens, ester is converted into alcohol with lithium aluminum hydride, and then alcohol is converted into aldehyde with oxidizing agent, that is CrO3. In the next step, now you are doing the Wittig reaction because you have aldehyde here, and this is the ylide. This ylide reacts with aldehyde to give you alkene. And in the next step, you react this alkene with KMnO4. Why KMnO4? Because we want to do dihydroxylation. We want to make diols from alkenes, and in order to make diols, we react alkenes with a strong oxidizing agent such as KMnO4 that will oxidize alkenes into diols. And in the last step, we remove this protecting group in the presence of acid, and then we will have a ketone here, and then we will have a cyclization product. We will have this this reaction between these two OH groups, and you will get the target molecule. Okay. Let's move on to the further examples. Now if you see this compound 1, 2, 3, 4, so the relationship of functional groups in this molecule is 1, 4, and the functional group that is present at position 1, that is ketone, and the functional group that is present at position 4, that is also ketone. So the relationship of functional groups in this molecule is 1, 4, and the nature of functional groups is carbonyl groups. So we call them 1, 4 dicarbonyl compounds. And if we disconnect this compound from 2 and 3 position, then we get A as an enolate, negatively charged, which will act as a nucleophile, and then B, which contains a positive charge, which will act as a electrophile. So for example, if you look at this compound, this is 1, this is 2, this is 3, and this is 4. So the relationship between these two functional groups is 1, 4. At one position we have ester, and at ester is a functional group of organic chemistry, and ester, and at 4 position we have ketone. In order to proceed with the retrosynthesis of this molecule, what we can do is we can disconnect from this position 3, 2 and 3, and one side gets the negative charge and the other side becomes electrophile, and this bromine we add as a good leaving group, and the carbon, that is bromine, is attached with this carbon, and this carbon is an electrophile. Now we react this cyclohexanone with a base. What happens is this picks the proton from here, generates a negative charge, and then this negative charge attacks on this carbon, and then bromine leaves. You get this product. But instead, if we how this happens is you have this bromoester or chloroester. The methoxide deprotonates this hydrogen, and you get this intermediate. Instead of cyclohexanone attacking this position, this compound attacks the cyclohexanone, and you get this product, which is wrong, because the desired product is this one, not this one. Okay, let's see how we can get the desired one. So there's the thing that you guys need to understand a bit, because cyclohexanone in this case, the enolate generated here is not that strong. So first what we need to do is activate the enolate. So activation of enolate is called, or make the enolate more nucleophilic by using the in-amine strategy. So first we add an, instead of directly generating enolate on the cyclohexanone, we generate the in-amine functionality. So this is called activation of enolate. And now this is your in-amine. Why? Because if this is your in-amine, this is in and this is amine, so it contains two parts. Amine because of this nitrogen, amine, or some say amines, or some say amines, and this contains double bond, and that is called in-amine. Okay, so this is in-amine. Now this cyclohexanone reacts with in-amine to make the first the lone pair of this nitrogen attacks on the electrophilic center of this carbon, and so the lone pair of this nitrogen attacks on the carbonyl carbon, and you get this compound, and in the next step there is a transfer of proton. So this oxygen picks this proton and you get this compound, and then in the next step you shift the lone pair of this nitrogen towards inside, and this water acts as a good leaving group now, and you get this in-amine protonated one. And in the last step you are transferring this tautomerism. This is the transfer of proton. This proton goes inside the cyclohexane ring, and this double bond shifts toward the nitrogen, and now you have this in-amine because it contains two functional groups. So one is in and another is amine. So in because of the double bond and amine because of the nitrogen. Now if you look at the synthesis of this compound, this is the cyclohexanone which reacts with secondary amine. Then in-amine is formed, and in that now this in-amine acts as a strong nucleophile. It's an electron rich species. Now it can attack on this electrophilic center, and then chlorine leave, and we get this product. And in the last step, we remove this in-amine functionality by reacting in the acidic media to generate the ketone. Now there was an issue. We couldn't use directly cyclohexanone because in the presence of base we get this product, but we wanted to prepare this compound. So in order to do this, we need activation, and for activation we introduce the in-amine functionality, which increases the electron density around this nucleus. Now in the next part, you can see that this is working very well in that case. And so because we are introducing the nucleophilic character inside the cyclohexanone. Okay, now what happens is you generate the target molecule. Let's move on to the next example. Now again, if you look at this compound, it's very simple to synthesize, but people will find it very difficult because they follow different strategies. So first thing first, recognize the functional groups. It's alpha beta unsaturated ketone. So we disconnect this from double bond position and the ring opening will take place. And if you count the relationship between these two functionalities is 1, 2, 3 and 4, and the nature of the functional group is they are carbonyl compounds, or they are precisely ketones. The relationship is 1,4 diketones. Now you can disconnect the CC bond from carbon 2 and 3, and one side you will get the cyclohexanone, and on the other side you will get the alpha chloroketone. So this is called alpha bromoketone or alpha chloroketone. This is the cyclohexanone. Now again, we shouldn't be doing the same mistake. We cannot use cyclohexanone directly to generate the enolate, but instead of that, we can do is generate in-amine first, reacting the ketone with secondary amine in the presence of acidic media. That will give us in-amine. Like now this is the more activated nucleophile because it contains the in-amine functionality. Now if you react this compound with this, now what will happen, this nitrogen will supply extra electrons there, caltonates electron, and this benzene, this double bond will attack on this position and bromine will leave, and you will get this product. Not directly, but in last step we need to do hydrolysis of this carbon double bond nitrogen to generate back the ketone. The purpose of adding this, making this in-amine, is to make the carbon enolate more nucleophilic in nature, stronger nucleophilic in nature. Okay, so this is your target molecule now, TM175. Now let's look at the another compound. This is the relationship between compounds is 1, 2 and 3 in this direction. If we go 1, 2, 3, this is the 1,4 relationship, and if we go from this side 1, 2, 3, 4, this is 1,4. Either it's 1,3 as well as 1,4 relationship. So we will consider 1,4 relationship first, and these are the two ketones, 1,4 diketones, and we can disconnect from the CC bond. So the relationship between this ketone is and this ketone is 1,4, and we disconnect from carbon between carbon 2 and 3 position. So this side will act as a nucleophile, and this side it will act as an electrophile. So this is the alpha position, and this is alpha bromoketone. Now this negative charge is stabilized. We don't need to further stabilize this negative charge, and we do not need in-amine now. Why? Because this negative charge is stabilized due to the electron withdrawing nature of the ketone and the electron withdrawing nature of ester. Now if you look at this ketone functional group, it contains the alpha position, which is this one and this one. You do bromination first at the alpha position. So you introduce bromine at alpha position, and in the next step you generate the enolate ion on this position, negative charge, which attacks on this alpha position of ketone and bromine group leaves, and you will get the target molecule. That is this one. Okay, let's move on to the next example. Again, you recognize the functional groups. There is two functional group presents. Now you decide the relationship between functional groups is 1,4. So at 1 position we have alcohol, and at 4 position we have ketone. So the first thing first, we have recognized the functional group nature of these compounds. So alcohol and ketone, they are present, and the distance between these two functional groups is 1,4. So 1,4 difunctionalized compounds we have. Now again we can disconnect this compound from carbon 2 and 3. So this is the carbon 2 and this is the carbon 3. It doesn't matter which way you do numbering, and this is not the nomenclature. You can say this is carbon 2 and you can say this is carbon 3. Okay, it doesn't matter. So you disconnect the CC bond, and the one side is become cyclohexanone and the other side will become the epoxide. Now this cyclohexanone again is not a strong enolate, because this negative charge is not stabilized by any group. So in order to make this negative charge a more stable, or in order to generate a more powerful nucleophile, what we will do is we first make enamine from the cyclohexanone. That is this one. This is the enamine formation, and in the next step the enamine attacks on this position and the ring opening takes place, and we get the target molecule 179. So that is the strategy to make these compounds or do the retrosynthesis of the 1,4 difunctionalized compound. So the extra step that you need to learn is to activate, don't forget to activate the cyclohexanone. That is target molecule 179. Now if you look at the another example, that is this target molecule, and first you recognize the relationship between the functional groups is 1, 2 and 3. If you go in this way, 1, 2, 3 and 4. So that is 1,4 relationship in this way and 1, 3 on that way. So we consider 1,4 relationship, and we disconnect this CC bond and we generate a negative charge here. And now we do not need to do any enamine activation. Why? Because this negative charge is already stabilized by the electron withdrawing group ester, this one. And then in the synthesis, when we will do synthesis forward direction, we react this compound with base, because this unit again is very familiar, you should be know. This is called actomethylene. This is active methylene unit. Now you generate a negative charge by using a base, and that negative charge will attack on this epoxide. But instead of getting this product, you will get compound A. Okay. So in the next is what you can do is do the hydrolysis. You're opening the ring, and then you will get the carboxylic acid on one side and the acid group on the other, and then you remove the extra acid group by doing heat decarboxylation, and then you convert OH into Br. So for example, this is the 1,4 relationship between alkyl halide and ketone. This is 1, 2, 3 and 4. So if you do first FGI, convert this bromine into OH, and then in the next step you disconnect this bond from here. You get epoxide and acetone, and you activate this acetone with ester and react this with base and generate a negative charge, attack on this epoxide. Instead of getting the target molecule, you get this. Now you do first hydrolysis. Hydrolysis will convert this ester into carboxylic acid and alcohol, and then you remove the carboxylic acid by decarboxylation by using 2, and then you at the end you replace alcohol with Br, and you get the target molecule, which was this one. Okay, so I hope you like this concept, and we will continue from target molecule 185 in the next video lecture. Thank you for watching. If you have any difficulty or if you need any organic chemistry books, please drop your emails below in this video. I'll try to reply your comments section, and don't forget to subscribe and share the link with your friends. Thanks for watching. Take care. Bye.